In this video, I'm going to talk about a few of the elements that are important in biology. So what you're seeing here is the NIST periodic table of elements. The table has 118 different elements, and we're only going to talk about 11 of those that are the most important in biology. I think it's interesting to see that the majority of the elements are classified as metals or metallic. So we'll have a handful of metal ions that are important, and then the most of what we're going to talk about are non-metals. So here's Beckett-Moll view, and I'm going to just start drawing a few, just kind of pick out the few elements that I'm going to talk about. We'll just start with the smallest atomic number. So hydrogen should be very familiar to people. Carbon. I'll just grab pretty much one of each to give an idea of what we're talking about here. Oxygen. Sodium. Calcium. I should have put down magnesium. Sorry about that. I'm now off the chart in random order. So we might as well grab potassium here. So this might be confusing. Here's hydrogen, and we grabbed these four elements here, along with carbon, nitrogen, oxygen. So next, phosphorus, which we'll just show as a phosphate ion. Sulfur, which in biology wouldn't be in this, I forget the name of it, but this is not a biological molecule here, S2H, SH2. And chlorine. So let me see if I lied or if I'm right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 elements that are the most important in biology. And I'm mostly thinking about humans. There's going to be different random, less mainstream organisms that might not adhere to this list here. But the elements I just went over or threw down are the top 11 in this list here of the composition of the human body. So this is sorted by mass, and I believe the total is 100. I didn't see it listed anywhere, but by mass, oxygen is the most abundant in the body. We breathe oxygen, but we also just get oxygen in our body from water. these should all be fairly familiar to everybody. Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. And they're all essential in the human body. And this table here, or this column here, explains kind of the basic use or where it comes from. Carbon is the main molecule, and it's able to form 4 different bonds. This isn't really the best view of everything, but here's carbon over here on the right. There's a little methane, CH4. And that's kind of this, 4 bonds is what you need to actually become 3-dimensional. So if you had just 3 bonds, you could fit flat on a sheet of paper. It's really when that 4th bond comes in that you are able to, once they're kind of hydrogens separate themselves to minimize energy, it's going to be taking up 3 dimensions. So carbon is making 4 bonds. Nitrogen is going to make 3 bonds. Phosphorus usually you would think makes 3 bonds, but it actually does well with this 5-bond situation as long as one of the bonds is a double bond, maybe just the oxygen. So it's this kind of configuration that phosphorus can exist in a stable form. Oxygen is going to make 2 bonds. Sulfur, 2 bonds. Chlorine is going to be a negative ion. Sodium and potassium will be positive ions. And hydrogen can sometimes be positive. I drew it here as like it wouldn't show up in the atmosphere, but it can also be down here as a positive ion, especially if you had an acid, you'd lose a proton, which is just this positively charged hydrogen. Sodium, potassium, hydrogen are going to be +1, and magnesium and calcium are going to end up with a +2 charge, as you can see here. You're probably familiar with NaCl. It seems to probably come up a lot, but table salt is going to be this. It's not a molecule, I don't think. It's just a collection of ions all forming a mass, I guess. So here's just the same abundance in the human body, but kind of showing it on the periodic table. So it's calling here the 4 basic elements: carbon, nitrogen, oxygen, and hydrogen. Quantity elements are going to be phosphorus, sulfur, chlorine, sodium, magnesium, potassium, calcium. And then you have a variety of elements that I'm not going to talk about, but there's trace elements and stuff that maybe it's an essential trace elements. but then you'll have things that are non-essential but still useful, maybe. Some of it maybe is debatable. But, these are all things that should be in your diet, either as supplements or just part of a healthy, well-balanced diet of vegetables and fruits and other things. So the reason that these elements are in your body is that they're also in the crust of the earth. So you can see the same elements: nitrogen, carbon, sodium, oxygen, sulfur, potassium, phosphorus, chlorine. They're all readily available in the Earth's crust. So carbon here is probably also familiar as carbon-14, a radioactive isotope. So just on the carbon page in Wikipedia, you can see that carbon-14 is a very low abundance trace element. It's radioactive, so it's going to release a high energy electron with this beta minus decay. And the half-life is around 5,730 years. And it decays into this nitrogen-14. So since it lost a negative charge, it has to gain a positive charge and go from carbon, which is atomic number 6, to nitrogen, atomic number 7. So it goes from 6 protons to 7 protons when it loses that electron. So this is a chart. I went too fast there. Abundance of chemical elements. And this is the chart showing where the elements came from. So hydrogen, helium, a little bit of lithium in the Big Bang. Everything else is created through various stars, low mass stars, exploding supernovae or whatever. So it shows up here carbon. How you get carbon is exploding massive stars or dying low mass stars. And that kind of throws a wrench into carbon dating, because if while an organism is alive, it's exchanging carbon with the atmosphere, and when it dies, it stops exchanging carbon with the atmosphere. And if all the radioactive carbon in the organism and the atmosphere was decaying at the same rate, then you wouldn't be able to tell any information about the age of the amount of time that's passed since the organism died. So the way carbon dating works is that cosmic rays generate carbon-14. So here's the carbon dating wiki page. And it says here, carbon-14, radioactive carbon-14 is being created through cosmic rays bombarding the atmosphere. And when they hit nitrogen, they are able to convert it back into carbon. I'm not sure the details on that, but if you were to slam nitrogen with a high energy electron, maybe that would be the right cosmic ray to get it to shift back into carbon-14. So the table I just showed you isn't complete. There is a way of making carbon through cosmic rays, which might be so minuscule amount of it that they didn't show it on the chart here, but it is the source of radioactive carbon. So a couple other radioactive elements, phosphorus. There's phosphorus 32 and phosphorus 33. Either one is going to have a beta decay with a 2 or 3 week half-life here. And radioactive sulfur, sulfur 35, beta decay 87 days, turning into chlorine. So phosphorus is an element that's in DNA but not in proteins, and sulfur is an element that's in proteins and not in DNA. For experiments that need to track where DNA is going and where protein is going, you can label one or the other and then see which materials stay radioactive and which materials are no longer radioactive. This is kind of a side note, but sodium, Na, is Latin for natrium, and potassium, K, the symbol K, is Latin for kalium. I'm not sure the source of those words, but natrium, I think of nature, and kalium, I think of California. So if it's easier just to remember the symbols from the Latin names, you can do that. I think that's everything I want to talk about. I guess just a quick summary. These are the 11 elements here. I can list them again. Hydrogen, carbon, nitrogen, oxygen, sodium, magnesium, phosphorus, sulfur, chlorine, potassium, calcium. And again, I didn't really go into where they are used, but this table here can give you that information.